Welcome back to the September 25th video talking about probably, to be honest, probably my favorite part of this course, what I as a student thought was the most fun part of the course, which is 11.3, talking about something called partial derivatives. And so by the end of the day, our goal is to be able to calculate the first partial derivatives of multivariable functions and then relate the sign, positive, negative, 0, of those derivatives to the contour map of a multivariable function to, in case we don't have the equation of a multivariable function, still be able to say something intelligent about what the derivatives are doing. So let's go ahead and get started with an informal definition. What is the partial derivative of f of x, y? And we're going to add a little extra specificity here. The partial derivative of the function with respect to the variable x in particular. Nothing to do with y, not yet. Now this is denoted in one of two ways. First is either this curved d, this is called partial. This symbol is called partial. Partial f over partial x. This is also sometimes called f with a subscript of x. And so this is kind of like df dx or f prime of x, except it's dealing with this fact. The notation is dealing with the fact that we have two variables here instead of one. Now the partial derivative of f of x with respect to x functions a lot like the regular derivative from Calc 1. The regular derivative represented a rate of change. As you change your input, increasing it just a little bit, what's the corresponding effect on the output? If you increase the input a little bit, what does the output do? Does it go up? Does it go down? Does it stay the same? Does it go up really fast? That's what the derivative told us, a rate of change. Now, the partial derivative is also telling us a rate of change as the input changes. But because the input has two parts, there are two primary ways to change the input. Change x a little bit, or change y a little bit. And the partial derivative of f of x with respect to x asks, how does the output change as you adjust x a little bit in the input? This is the rate of change of the output f of x, y as x changes, leaving y constant, leaving y unchanged. Just change your x a bit and tell me what happens to the output as you change your x a little bit. Now we have the corresponding partial derivative with respect to y, which is denoted partial f over partial y, also f sub y. And as expected, this is the rate of change of f of x, y as you increase y a little bit and leave x alone. Don't change x, only change y and see what happens to the output. Now just a heads up, I've given you the two most common notations for the partial derivative and the ones that I will be leaning on and using most often in the class. But if you go to our textbook, if you go to Stewart, page 758, you can see a big list of different notations that are in use for the partial derivative. This is a very blurry scan right here, just to give you an idea of the variety of notations which are in play. But the ones that we will be focusing on and using the most often are the two notations that we gave above, which are this one and this one. Okay, now that we've established in concept what the partial derivative is telling us, let's discuss how we could actually calculate it from the equation. And the idea is very, very neat. The idea says, hey, in the partial derivative with respect to x, we're supposed to leave y constant. So what if we just took the derivative with respect to x in the formula for f of xy, and let's just take it the same way that we did in Calculus 1, and let's just pretend like y is a constant number. Take the derivative of f of xy with respect to x, treating y as an actual constant, as a number. Same thing for f sub y. If you want to take the derivative with respect to y, just do it as you would in Calculus 1 and pretend like the other variable x is just a constant number. Take the derivative with respect to y, pretend it's the only variable, and pretend that x is constant. Let's do an example to make this concrete. So here we have the function f of xy equals 3x times exponential of 5xy. Let's calculate the partial derivative with respect to x and the partial derivative with respect to y. So let's start with the partial derivative with respect to y, to x rather. In this case, I'm going to pretend that y is constant. So that means that the y in this formula is going to behave exactly like this 5, like this 3. So I'm going to call all the constants blue. Our variable is x, and everything else is a number. And now, pretending that y is just a number, I'm going to go ahead and take the derivative of this with respect to x, just like I did in Calculus 1. Now, this expression has a product of two different functions of x, 3x times e to the 5xy, which means we're going to need to use product rule. So I'll do first 3x times the derivative of the second, which is e to the 5xy. And actually, since we're just getting started, I'm going to try and be a little careful about the colors here, just to really emphasize who is a constant and who is not. Now we also have a second term where we take the derivative of 3x and multiply that by e to the 5xy. Okay, now let's perhaps deal with the second term first, since I think it is a little easier because we are probably accustomed to taking the derivative of something like 3x by the power rule that quantity is just 3. In this first term though, when we take the derivative of e to the 5xy, we'll need to use chain rule for that. Now imagine for a minute that we just had 5x. When we take the derivative of e to the 5x, chain rule will cause that constant multiple of 5 to come down to the front. But because we're treating y as a constant, we will do exactly the same thing with y that we did with 5. So here's our 3x leading. We're going to multiply it by, here is our original exponential, 5xy, And then because of chain rule, the two constant multiples, 5 and y, will come down to the front. Take the derivative with respect to x, pretending like y is a number. And we get the result that the partial derivative of f with respect to x is equal to 3x times 5y e to the 5xy plus 3 e to the 5xy from product and chain rule. All right, let's try then to take the derivative of f with respect to y, which means that we are pretending like x is constant. Excuse me. Pretend x is constant. So I'm going to go through and do a little color coding. 3x, e, 5x, there's only one instance of a variable in this calculation. All the x's are being treated as constants, and so the only variable I have is this y in the numerator of the exponential. Which means that I can essentially ignore the 3x in the front because of constant multiple rule. 3x is a constant multiple because the x is constant. And it can be ignored, brought directly out to the front, and I can think just about the derivative with respect to y of the exponential portion in the back. Now, to calculate the derivative of the exponential portion, the reasoning is the same that we used when we were looking at df dx. The chain rule causes the constant multiple of 5x to come down to the front. So we have 3x times 5x e to the 5xy, or after simplification, 15x squared e to the 5xy. And that would be the derivative of this function with respect to y. Now notice that these are very different looking answers. 15x squared, 5xy only has one term, whereas the partial derivative with respect to x has two terms. And you can usually expect that to be the case. Usually the partial derivative with respect to x and the partial derivative with respect to y are going to look quite different. Okay, let's get a little bit more practice, and this time let's practice with a function of not 2 variables, but actually 3 variables. Let's see what it might mean to look at the rate of change in the x direction, the rate of change of the output as y changes, and the rate of change of the output as z changes. So let's go ahead and get started with partial f, partial x. Now in the 2 variable case, when we were calculating df dx like this, we pretended that the other variable, y, was just a number. It was being held still. It was being held constant. In this 3 variable case, when we calculate df dx, partial f, partial x, we are going to pretend that the other 2 variables are constant. Y and z are both constant. Everybody except x, we are pretending is just a number. So that means that in terms of color coding our function, the only time x appears, the only time a variable appears is this x squared here in the front. Y cubed is a number, z to the 4th power is a number. So now let's take the derivative of natural log of x squared plus number using the chain rule. the derivative of natural log of something is equal to 1 over that something. And then we need to make sure to multiply by the derivative of the inner function. We've used chain rule here. Now the derivative of the inner function with respect to x can be taken one term at a time. The derivative of x squared by the power rule is going to be 2x. Now what's the derivative of y cubed? Well, in this calculation, y is a number. Y cubed is a number. And because of that, the derivative of that constant is 0. Likewise, the derivative of z to the 4th power is 0, because z to the 4th power is constant in this calculation. So, having calculated the derivative of the inner function, multiplied it by the derivative of the outer function, we obtain the partial derivative 2x over x squared plus y cubed plus z to the 4th power. Now, I would like you to pause the video and try on your own as an exercise to see if you can calculate the partial derivatives of the same function with respect to y and z. Try it on your own and then we'll do it together. Alright, I'm assuming you've paused it, you've given it a shot. Now let's do it together so you can check your work. The partial derivative with respect to y treats x and z as constant. So if I take the derivative with respect to y of this natural log of x squared plus y cubed plus z to the 4th, then the process will be almost exactly the same, except when we apply chain rule to take the derivative of the numerator, then instead of taking the derivative of x squared using the power rule, we'll be taking the derivative of y cubed using the power rule. The derivatives of x squared and z to the 4th power will vanish because both of those are constant. And likewise, if we want the partial derivative with respect to z, which treats x and y as constant, once again, chain rule will cause the entire inner quantity to go to the denominator. And then if I take the derivative of the inner function, x squared vanishes, y cubed vanishes, and the derivative of z to the 4th power with respect to z will be equal to 4z cubed by the power rule. So I think that the most challenging aspect of this section is that you sort of have to mentally do this coloring process as you calculate these partials. In your first pass through the problem, when you're doing partial f, partial x, you'll be thinking of x as the variable and everyone else as a number. But then your mind has to switch tracks. Think of y as the variable and x and z as numbers, and then you have to switch track again and see z as the variable and x and y as numbers. So there are a few mental gymnastics involved, but I do find these problems very satisfying once you sort of get into the swing of things. Now, from time to time, as in this example, we will once again not be given the equation for the function f of xy, which means we'll no longer be able to find formulas or find exact numbers for the partial derivatives. But with this contour map on the side, we can still actually say something about the sign of the partial derivatives, whether or not the partial is going to be positive, negative, or 0. So to begin with, they're asking us to consider the partial derivative in the x direction at the point 1, 0. So let's go ahead and locate that on our graph. 1 in the x direction, 0 in the y direction would put us right on top of this right-hand z equals -1 level curve. Now let's imagine that from that point, we're going to increase the input ever so slightly in the x direction, which in the level curve amounts to starting from this point, 1, 0, and moving a little bit directly to the east in the positive x direction. Look at what happens to our position in the contour map when we move from this point a little bit to the east. We started on the level curve, z equals -1. But now we're moving toward the level curve, z equals -2. So let's just jot down some thoughts. We're moving from z equals -1 down to a lower z value of z equals -2. So we increased x a little bit, and as a result, our output went down a little bit. Because the function's output decreased in the positive x direction, the function is decreasing in the positive x direction, and its partial derivative has negative sign. Decrease, negative derivative, exactly the same as we saw in Calculus 1. Increase, positive derivative, decrease, negative derivative. Okay. Now let's suppose that we try and calculate exactly the same derivative, the derivative with respect to x, but our starting position is on the other side of the graph. So I'm going to go ahead and erase our original mark so we can put a new mark on at the point -1, 0. And we're still going to be moving ever so slightly in the positive x direction. So let me mark that with a little arrow to the east from the starting position of -1, 0. Now, do you have a guess about what the sign of this derivative is? We're moving from z equals -1, same value on this level curve to the left-hand side, but this time moving to the east will get us closer to the z equals 0 level curve. So that causes the output to increase from -1 toward 0. As a result of that, the partial derivative in the x direction at this left-hand point is greater than 0, because as we move to the right from that point in the positive x direction, our z values, our outputs are going up. Our function is increasing in that direction. Now here I think is the hardest one. What about f of y in 1, 0, the point 1, 0? So once again, we're back on the z equals -1 level curve at the point 1, 0. Now, this is the moment where we need to acknowledge that the change in y is supposed to be practically nothing. When we do these calculations of the change in f divided by the change in y, the change in y is supposed to be so small that it's practically nothing. When we were studying Calculus 1, we understood this by taking a delta x and taking the limit as delta x approached 0, so that x was barely changing at all. And in this case as well, x is barely changing at all. Y is barely changing. Now, let's have a very close look at this curve. At the point 1, 0, if I travel in the y direction, that vector pointing straight up in the y direction is actually tangent to this level curve. In y direction, tangent to level curve. And what this means is, because the movement in the y direction is tangent to the level curve, if you move really small amount in the y direction, you're pretty much still on the same level curve that you started on. So here's a general principle that sometimes I just have to use without thinking too much about it, which is that if level curve is tangent to the vector 0, 1, positive y, then f sub y is going to be equal to 0, because your function is pretty much still on the level curve that it started on. And because of that, the function's value will remain essentially constant. We'll see essentially no change at all. Corresponding to that, if the level curve is tangent to the vector in the positive x direction, then the rate of change in the x direction is going to be 0 at that point, because moving just ever so slightly in the positive x direction will pretty much not cause you to leave the level curve that you're already on, and your output value will remain essentially constant, so that your derivative is 0. Therefore, in response to this question, my final answer would be that this partial derivative is 0, because at this point, the positive y direction and the level curve are tangent to each other. So just bear that in mind. For myself, mentally, I always sort of envision this movement in the y direction as way too big. And if you think about the movement in the y direction as something that's that big, then it will look like you're moving from the z equals -1 curve to the z equals 0 curve. So for me, I always have to bear in mind that the arrow in the y direction, these movements are extremely small. And if you move for a very short distance in the y direction, you're basically staying on that level curve, and your output value is not changing. Okay, so tomorrow we're going to talk a little bit about the multivariable versions of our higher order derivatives from Calc 1. The things like second, third, fourth derivatives, where we had all those primes attached to our function. And that's what tomorrow is going to be about.